Hello everybody. In this video we're going to study the method of variation of parameters. This is also a non-homogeneous linear differential equation, like we did in undetermined coefficients. For this differential equation, we're going to use these ingredients. We're going to need Wronskian determinant, and we need how to solve by particular part using this formula. I'm not going to show how we derive this formula because the purpose of this video is to use this practically. So I might make a separate video about how we derive this formula. Before we start problem number 21, I would like to compare this with the previous method. In undetermined coefficients and variation of parameters, we start with the same equation. And in variation of parameters, our y prime coefficient has to be 1, so we divide everything by p of t. So we need to clear the coefficient of y double prime if it is not 1. Y homogeneous part is the same for both, so we convert it into characteristic equation and then solve the quadratic function. And y particular part, for variation of parameters, we use the formula above, and for undetermined coefficients, we use our guess function as we did in video part 2. So disadvantage of variation of parameters can be computing the integrals. Some of the integrals might not be easy to compute. So let's start with one problem and see step by step how we are doing. So our first step is to find homogeneous part. We check that our y double prime coefficient is 1, so we are good to start. So this is r squared minus 3r plus 2 equals to 0. And from here, r minus 2 times r minus 1 are the roots, and r1 is 2, r2 is 1. Now we can write our y homogeneous part. Y homogeneous is, this is 2 real roots, so c1 e to the x from here plus c2 e to the 2x from here. And in this y homogeneous part, e to the x is our y1 and e to the 2x is our y2. So we labeled our y1 and y2 so we can find our Wronskian determinant. For Wronskian determinant, we need y1, y2, y1 prime, and y2 prime. Our y1 is e to the x, our y2 is e to the 2x. Derivative of e to the x is e to the x. Derivative of e to the 2x is 2e to the 2x. Now we're going to take the determinant. When we are taking determinant, entry A times entry D minus entry B times entry C. So determinant is equal to A times D minus B times C. So we're going to do the same thing here. So red diagonal minus blue diagonal. So we're going to have 2e to the 2x times e to the x minus e to the x times e to the 2x. So here we have e to the 3x, 2e to the 3x minus e to the 3x. So we obtain e to the 3x as our Wronskian determinant. So we have our Wronskian as well. Now we can plug everything in our y of p formula. Before we start, I would like to rewrite the ingredients. We had y1, which is e to the x. We had y2, which is e to the 2x. We need our Wronskian determinant, which is e to the 3x. And we need our g of x, which is in our original problem, e to the 3x. Now we can plug everything in. Yp is equal to negative y1. y1 is e to the x, so negative e to the x, times integral of y2 e to the 2x times g of x, which is e to the 3x, divided by Wronskian determinant, plus y2, which is e to the 2x, times integral of y1 times g of x, divided by Wronskian determinant. These cancel each other, and we're going to take this integral and multiply by negative e to the x. Integral of e to the 2x is 1/2 e to the 2x, and we multiply it by negative e to the x. So from here we obtain 1/2 e to the 3x negative. Now we're going to do the right hand side. This cancels. Integral of e to the x is e to the x, and we multiply it with e to the 2x. So we obtain e to the 3x. Now we're going to add these two up. Negative 1/2 e to the 3x plus e to the 3x makes 1/2 e to the 3x. Now everything is ready. This is our y particular. So y general is equal to y homogeneous plus y particular. Our y general is c1 e to the x plus c2 e to the 2x plus 1/2 e to the 3x. So this is the solution for the given differential equation using variation of parameters. Then the derivative of w will be y double prime. So this is our dw dt. Now let's write everything in terms of w. So we have 2t w prime equals to, and this is our w, so we can take it to the other side of the equation as positive. And instead of w prime, we can write dw over dt. Now if we multiply both sides by dt, we obtain 2t dw equals to 3w dt. We would like w term on left hand side and t term on the right hand side. So we divide both sides by 3w and 2t simultaneously. So we obtain 1/3 w to the negative 1 dw equals to 1/2 t to the negative 1 dt. Now we can integrate. Integral of 1 over w is ln of w. And integral of 1 over t is ln of t. Now, using the logarithmic rules, we can bring this as the power of w, and we can bring this as the power of t, and we know that e to the ln of x is equal to x, whatever this argument is. So we can take to the e on both sides, and our argument is w to the 1/3 equals to t to the 1/2 plus c. And we're solving for w, so we can multiply both sides by the power of 3 over 1. And we can bring c in front of t. So w is equal to ct to the 3 over 2. This is our w. W was v prime. So if w is v prime, then we can solve for v here by integrating one more time. Integral cancels the derivative, so v is equal to, here we can apply the integration rules, add 1 to the power and divide it by the power. Dividing by 5 over 2 is multiplying by 2 over 5, and this is going to be 5 over 2. This is our v. This is our v of t. and we have plus k here. As in the repeated root case, we can pick up c value and k value arbitrarily, whatever we want, to eliminate the extraneous roots. So here we arbitrarily pick c as 5/2, so we can cancel out this, and we can pick k as 0, so our v of t will be equal to t to the 5/2. At the beginning we said that y2 of t is equal to v of t times y1 of t, and our v of t is t to the 5/2, and our y1 of t is given as t to the -1. If we do this multiplication by adding the powers, we obtain t to the 3/2. Now we know our y2 value and y1 value, so we can make up our general solution. Our general solution is y1 of t plus y2 of t. So it will be c1 t to the -1 plus c2 t to the 3/2 as our general solution to this reduction of order. So here is the general idea for reduction of order. At the beginning we have non-constant coefficients equation, and our y1 of t is given, so we guess y2 of t as v of t times y1 of t. So we prepare the derivative and the second derivative of y2 of t, which was v times whatever the initial given y1. And then after we prepare the derivatives, we plug in original equation. We distribute and simplify carefully, and we get rid of v term as a result, and we obtain some v double prime plus v prime kind of term, and we apply change of variable and turn it into first order ordinary differential equation, and then we apply ordinary differential equation techniques. It could be separable, integrating factor, etc. So this is the guideline that you need to follow for reduction of order. Problem number 22. We have y double prime minus y equals to 2x squared minus x minus 3. First we start by checking the coefficient of y double prime. The coefficient is 1, so we are good. If the coefficient was not 1, we had to clear it, divide each term by the coefficient of y double prime, so make it 1. And our g of x is given here. This is our g of x. We start with y homogeneous part. Our y homogeneous will be r squared minus 1 equals to 0 when we convert this into characteristic equation. Solving for r squared equals to 1. From here r equals to plus or minus 1 when you take the square root on both sides. Now this is repeated roots, so our y homogeneous will be c1 e to the x plus c2 x e to the x, because it is repeated roots. Now our next step is to label y1 and y2 to be able to find Wronskian determinant. For our Wronskian, we need our y1, y2, y1 prime and y2 prime. y1 is e to the x, derivative of e to the x is e to the x. y2 is x e to the x, derivative of x e to the x is the product rule. So let's make it here. When we take derivative of this, we need f prime times g plus f times g prime, where x is f, e to the x is g. So f prime is 1, g prime is derivative of e to the x is e to the x. So f prime is 1 times g, which is e to the x, plus f times derivative of g, which is e to the x. So e to the x plus x e to the x is derivative of y2. Now we're going to take the determinant by multiplying this diagonal, subtracting this diagonal. E to the x times e to the x plus x e to the x minus e to the x times x e to the x. We are going to distribute e to the x times e to the x is e to the 2x plus x e to the 2x minus this is going to be x e to the 2x. They cancel out, so e to the 2x is our Wronskian determinant. Now we have our Wronskian y1, y2 and g of x, so we can plug in our formula. Let me copy our formula here. Before I start, as usual, I would like to write the ingredients. Our y1 was e to the x, our y2 was x e to the x, our g of x was 2x squared minus x minus 3, and our Wronskian determinant is e to the 2x. So our yp is equal to negative y1, negative e to the x, times integral of y2 x e to the x times our g, which is 2x squared minus x minus 3, all over e to the 2x dx. Plus, we have y2, which is x e to the x, times the integral of y1 e to the x times g of x, 2x squared minus x minus 3, divided by 2x e to the 2x dx. Now we start the tedious part, computing this integral. I computed this integral on the site. It took more than 10 minutes, so I'm gonna directly write down here. So you here do integration by parts twice integration by parts. Again, here you have to use integration by parts twice. So you have two functions in multiplication form, so you need to use integration by parts formula, which is u times v minus integral of v du. I have detailed video about how to compute integration by parts. So from the first integral, we obtain everything negative 1/2 2x squared plus 3. After computing the integral and multiplying negative e to the x. And from the second integral, we obtain negative 1/2 times 2x squared minus 5x plus 2. And if we add them up, we obtain negative 2x squared plus x minus 1. So this is our y particular. Now our y general is equal to y homogeneous part or y complementary part, whatever you guys are calling in your book, will be c1 e to the x plus c2 e to the x e to the x minus 2x squared plus x minus 1. And if you would like to prefer constant a and b, you can also use a and b instead of c1, c2, depending on your teacher's format. So this is our general solution. Again, variation of parameters have one drawback, which is computing tedious long integrals, like integration by parts. Let's finish the topic with this example. We start first by finding the y complementary or y homogeneous. So our characteristic equation is r squared plus 1 equals to 0. Now we're going to solve for r. R squared is equal to negative 1 and r is equal to plus or minus square root of -1. And square root of -1 is I. Now this complex number is 0 plus or minus I. So here our alpha is 0, our beta is 1I. So this is our beta. Let's remember, whenever we have the complex roots, e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. So here our alpha is 0 and our beta is 1. So our y homogeneous part will be e to the 0. Alpha is 0. 0 times x is 0. So e to the 0 is 1, so we don't need this term. c1 cosine of x plus c2 sine of x. So this is our y homogeneous part. And here our cosine is y1 and sine of x is y2. Now we can find our determinant. So our Wronskian will be y1, y1 prime, y2 and y2 prime. Our y1 is cosine of x and our y2 is sine x. Derivative of cosine is negative sine and derivative of sine is cosine x. Now we're going to multiply these two entries and subtract this entry. So cosine times cosine x is cosine squared of x minus negative sine x times sine x is negative sine x squared. So this is going to be addition, negative sine. Cosine squared of x plus sine squared of x is equal to 1 by the Pythagorean identity. So you need to know Pythagorean identity for these trigonometric functions. So our Wronskian is 1. Now let's plug everything in our formula. Our y1 is cosine of x, our y2 is sine of x, our Wronskian determinant is 1, and our g of x is tangent of x in the original problem here. Now we're going to plug everything in and compute the integrals. So our y particular will be negative y1, which is negative cosine of x, times integral of sine x times tangent x over 1. So we don't need to write. That is dx. Plus we have y2, which is sine of x, times integral of cosine of x from y1 times tangent of x dx. Let's start from here. Tangent is equal to sine x over cosine x. So we can express tangent as sine x over cosine x. And cosine cancels cosine, so we are taking integral of sine. So I would like to make the chart again. This is positive cosine direction, negative cosine direction, positive sine direction, and negative sine direction. If you go to clockwise, you get the derivative of each function. If you go to counterclockwise, which is this way, counterclockwise, then you get the integral of each trigonometric function. And if you go to clockwise, you get the derivative. So integral of sine of x is negative cosine of x. So from this integral, we get negative cosine of x. Let me write here. And we need to multiply it by sine of x. So cosine x, sine x. That's what we obtain from the second part. From the first part, we're going to express tangent again as sine over cosine. We have sine x here times sine x over cosine x instead of tangent, and we obtain sine squared of x on the numerator and cosine x on the denominator. Now we're going to express sine squared of x as 1 minus cosine squared of x using Pythagorean identity. Let me remind, sine squared of x plus cosine squared of x equals to 1, and from here if you solve for sine squared of x, it's going to be 1 minus cosine squared of x. Now we have cosine x, the common denominator for this numerator, so we can separate the integrals. 1 over cosine x minus integral of cosine squared of x over cosine x. Cosine squared of x over cosine x is just cosine x, and 1 over cosine x is secant x. Now you need to know integral of secant x by heart. This is one of the template integrals you need to know. So antiderivative of secant x is ln of tangent x plus secant x. I have a video about how we derived this, and antiderivative of cosine x is sine x. Now we're going to multiply this whole equation with negative cosine x. So it's going to be ln of tangent x plus secant x cosine x minus sine x cosine x. Because this was negative, so this is going to be negative and this is going to be positive. And on the second part, we obtained negative cosine x sine x. That will cancel this term here. So our y particular will be this. So this is our y particular. So our general solution will be y homogeneous, which is c1 cosine x plus c2 sine x. You can use AB if you would like instead of c1 c2. A cosine x plus b sine x minus ln of tangent x plus secant x times cosine x. So this is our solution for this differential equation. So variation of parameters requires to know trigonometric identities. I have detailed video about it. It also needs to know integration techniques, and you have to be fluent taking determinants. So variation of parameters will be good and fluent. Thank you for watching. See you at the next video.